Chapter 3.4, Equivalent Statements. So in this chapter, we're going to take all of the types of statements we've looked at before and sort of figure out how we can manipulate them so that we can say them in different ways, but still mean the same thing logically. So as a quick review, here are the 5 truth tables, the 5 different connectives we've learned about. The negation, which flips all of our truth values. The conjunction are and statements, which are only true if both are true. The disjunction, our or statements, which are only false if both are false. The conditional, our if-then statements, which are only false if they start true and end false. And the biconditional, our if and only if statements, which are true if the incoming values match. So, equivalent statements. 2 statements are equivalent, which is symbolized by 3 lines or a double arrow, which is, yes, the exact same thing that we use for the if and only if statement. So for our purposes, I will always use the 3 lines, but you may see in your textbook or in your in the homework the double arrow to mean the equivalent statements. But anyway, equivalent statements, if both statements have exactly the same truth values in their answer columns. So sometimes the term logically equivalent is used instead. So we're just expanding the term to mean it's logically equivalent. Doesn't mean that necessarily in English we would say this and it implies the same thing, but logically they are the same. So, if the answer columns are not identical, the statements are not equivalent. So if you're asked, are these equivalent statements, all you have to do is create the truth tables for both statements and see what's going on in the answer columns. So for example, we want to determine whether the following 2 statements are equivalent. So here we have P and the parenthetical Q or R, and P and Q or P and R. So what we're going to do is we're going to make a very large truth table here, where I've broken it down into this section here. This section here is the first statement, and this section here is the second statement. So we start with Q or R because that's our parenthetical, and there's no direct negation. So Q or R, we are looking at these 2 columns, and the or statement is only false if both are false. So where are both false? That's happening here and here. So we get our 2 false columns, our 2 false rows right here and right here. Next, we've got our and statement between P and this new column, and we have our and statements, our conjunctions, are only true if both are true. So we're looking for where are both of these columns true. And that's going to be here, 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 not there, nope, 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 and nope, right? So we get these 3 are where our statements are both true. Okay. So that's the final column of the truth table for this statement. Now we move on to the other statement, and we want to make P and Q, once again, only true if both are true. So P and Q, we're looking at these 2 columns, and we're looking for both being true. Both being true happens here and here, and that's it. So those are our 2 true values. Next, we have P and R, so that's these 2, nope, that's these 2 columns right here, and once again it's still an and statement, still a conjunction, so we're looking for both to be true. So where are both true? That happens here and here, and that's it. So those are our 2 true rows. Finally, we have our or statement between these 2 columns. Or statements, disjunctions, are only false if both are false. So we're looking for where are both false. So both are false here, 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 and here. So all of those are going to be false, with the first 3 being true. Now we ask the question, are they equivalent? Here's the definition as a reminder. Two statements are equivalent if both statements have exactly the same truth values in the answer columns. And in fact, they do, right? 3 trues and 5 falses, 3 trues and 5 falses, they're exactly the same. So these statements are in fact equivalent. So we can write our symbol, the equivalence symbol, right between them. Now what about verbal equivalence? So if we wanted to determine which statement is logically equivalent to the following, it is not true that the tire is both out of balance and flat. Well, the best way to do this is to put it into symbolic form, not leave it verbally, because verbal statements are confusing. Symbolic statements are a lot easier to work with. So, if we say P is the tire is out of balance and Q is the tire is flat, then the given statement, it is not true, remember, that's saying that the entire statement is false, so that's negating the whole statement. And then we have an and between our P, Q, gives us negation of P and Q. So now for each of these given statements below, we're going to write them symbolically. We're not going to be able to know which answer is right until we make their truth tables, though. So we have if the tire is not flat, then the tire is out of balance. So not flat would be negation of P. Not out of balance would be, Let me try that again. Negation of Q, not out of balance, will be negation of P. And then this is an if-then statement, so we put our arrow between them, like so. The tire is not out of balance, so that's negation of P. Or the tire is not flat, so that's negation of Q, like so. The tire is not flat, so that's negation of Q. And the tire is not out of balance, that's negation of P. If the tire is not out of balance, negation of P, then the tire is not flat, that's negation of Q. So now we have these 4 different statements, and we are going to compare the truth tables to the truth table for the original statement, like so. So for our original statement, we have P and Q, which we are then going to negate. So P and Q is only true if both are true, which means it's true in the first row. Then we negate each of these to get false, true, 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 and that's what we're trying to match with. So negation of Q implies negation of P. We're starting from our negation columns, which notice that I have already placed these on our table just for ease. So our negation columns, we're starting with negation of Q first, followed by negation of P. So we want, remember, we're looking for when does it start true, end false. That's when it equals false. So here it's true, here it's true, here it's false, here it's false. So this is the row where it started true and ended false. So that's going to be true, false, true, true. Next, we have our OR statement. Our OR statement is only false if both are false. So we look for where are they both false. That's happening right here. And so we get false, true, true, true. Next, we get negation of Q and a negation of P. So our AND statements are only true if both are true. So we look for where are they both true. That's happening right here. So we get false, 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 true. Then our negation of P implies negation of Q. So that's starting here, ending here now. Still the same thing where we want starting true, ending false. That's going to be our only false statement. So when do we start true? When do we end false? That lines up right here. So we get true, true, false, true. Now which ones are the equivalent statements? That's just which one matches our original. And that is, in fact, that second statement. So B is equivalent to our original. In other words, it is not true that the tire is both out of balance and flat means the same thing as the tire is not out of balance or the tire is not flat. So, this is actually a very important principle that we've seen before. We just saw it in a different way. This is De Morgan's law. So, we saw De Morgan's laws for set theory before, where we had our intersection, the opposite of an intersection is then a union, and then the opposite of a union is then an intersection, right? So the complement of A intersect B is the complement of A union complement of B. And the complement of A union B is the complement of A intersected with the complement of B. So when we complement an intersection, we get the complement of each individual united. And then the complement of a full union is the same thing as the complement of each individual piece intersected. Well, logically, we then get, instead of our intersection, we have our and statement. Instead of our union, we have our or statement. Instead of our complement, we use negation. But we're just changing the symbols. It's basically the same principle. Because logic and set theory are very similar, it just takes a little bit of thought to see how they work the same way. So we've seen this rule, we just proved it, but we also have the opposite rule, where the negation of P or Q is the negation of P and the negation of Q. So anytime you want to sort of distribute a negation into parentheses, you have to flip your symbol upside down, in the same way that when you want to distribute a complement, you have to flip the intersection or union upside down, essentially. So, if we wanted to write a statement that is logically equivalent to, it is not true that tomatoes are poisonous or eating peppers cures the common cold, we would start by identifying what are PQ. So P is tomatoes are poisonous, Q is eating peppers cures the common cold. So this statement has our negation out front and an or statement, so it's a negation of P or Q. By De Morgan's law, we know that this is equivalent to negation of P and negation of Q. So we can distribute this not truth to each piece as long as we change our or to an and. So tomatoes are not poisonous and eating peppers does not cure the common cold. So knowing this law is going to be very important for being able to answer what is a logically equivalent verbal statement as well. Now there are many other equivalent statements. We're going to talk about a few of them, but there are many, many more that we could find through truth tables, etc., and some that you might be able to figure out on your own. But the most important ones that we're going to see besides De Morgan's law are to change a conditional into a disjunction, we can negate the antecedent. Remember, the antecedent is just the first part. Change the conditional symbol to a disjunction symbol, and keep the consequent, the second part, the same. So in other words, if P then Q is equivalent to negation of P or Q. Then the negation of the conditional, using De Morgan's law, we can prove that we can that if P then Q is equivalent to negation of P or Q, we could say negation of P or Q would be equivalent to, distributing this in, we get P and negation of Q, which is what is right there. So, we have basically the negation of a conditional becomes a conjunction with the consequent being negated. So you cannot not distribute a negation into a conditional. It just doesn't work that way. It is not the same thing as negation of P then negation of Q. It just isn't. We can show this with truth tables. In fact, we're going to soon. It's just not the same. So, if we wanted to write a conditional statement that is logically equivalent to the cows are in the pasture or the horses are not in the barn, we're going to use this equivalence. So if P is the cows are in the pasture and Q is the horses are in the barn, then in fact we have P or negation of Q, which is not exactly this statement, right? But verbally what's going on is to change a conditional statement into a disjunction, we negate the antecedent, change the conditional symbol to a disjunction symbol, and keep the consequent the same. Which we can then do in reverse. We're negating the antecedent, which means we're just changing the whether or not the antecedent is negated. So in fact, this, we're going to renegate it instead of negating it. So this negates it, we're going to do the opposite. But it's already a, let's say, positive, so we're going to make it negative. We're just going to change its sign. Again, I'm using algebra terms here, but it works in a very similar way, right? A negative times a negative equals a positive. A double negation is a positive statement. So that's what we're going to do. So we're going to negate to go backwards. So here we get P or negation of Q becomes, we change the sign on the P and keep the consequent the same. To get negation of P, then negation of Q, which we can see works in the same way as this, where we change the symbol, right, and keep the same. So, verbally this becomes, if the cows are not in the pasture, then the horses are not in the barn. Now, why is that the same? It might take a little bit to sort of wrap your mind around how those mean the same thing logically or even verbally, but they do. So the cows are in the pasture or the horses are not in the barn means that one of these two things has to be true. So if this one isn't true, then that one has to be. That's basically how this works. If this one isn't true, so if the cows aren't in the pasture, then the horses have to not be in the barn. That's why they're equivalent. But we have truth tables to figure that out for us instead of having to really think it out. Next, let's try taking that negated conditional into a conjunction. So write a conditional statement that is logically equivalent to it is false that if you hang the picture, then it will be crooked. This should be write a conjunction statement, not a conditional statement. So write a conjunction statement that is logically equivalent to it is false that if you hang the picture, then it will be crooked. So we're going to start from our P, which is you hang the picture, and then Q is the picture will be crooked. So this statement, once again, it is false that means we're putting that negation out front, and then it's just a simple if-then statement. So a little bit simpler than our previous one where we had an extra not in there that we didn't want, etc. So in this case, I can just directly go to this other statement. I know what P is, I know what Q is, so I can say them, right? P is you hang the picture, and negation of Q, picture will not be crooked. So you hang the picture and it will not be crooked. So, in other words, these two things have to be true together. Whereas it is false that you hanging it would mean that it's crooked. Basically would be saying that you're going to hang it crooked. If you hang it, it'll be crooked. But I'm saying, nope, that's a lie. So, if you're hanging it, so in this case, that was a lie means that you hang it and it's not crooked. Alright, so all of that said, we're going to get down to sort of the real meat of this is all about different variations on conditional statements. And I don't mean how we can turn them into conjunctions and disjunctions. I mean how I've hinted at before that conditional statements tend to confuse people. because of the fact that they don't have a symmetry to them that we expect. So the conditional P implies Q, which is read as if P then Q, I'm going to give the example of if it is snowing then it is cold. I can turn this around and start negating things, and we can talk about which version of these is actually logically equivalent to the original conditional statement. Well, we have first the converse of this statement is when I just flip around P and Q. So I say if Q then P. So instead of if it is snowing then it is cold, I'm going to say if it is cold then it is snowing. So I'm just changing these. The inverse doesn't change the order but adds a not to both. So if not P, then not Q, is if it is not snowing, then it is not cold. And then the contrapositive, that's basically taking the converse and inverse together, so we're flipping the order and changing the sign, or adding a negation to both. So if not Q, then not P. If it is not cold, then it is not snowing. So let's think about this verbally. Which one actually makes sense to mean the same thing? So let's talk about when is this first one true, or is this first one true? If it is snowing, then it is cold. That feels true, right? If it's snowing, it has to be, freezing out, so it's cold. Okay? But the second one, if it is cold, then it is snowing. Is that true? No. I mean, as I'm recording this right now, it's pretty cold out, and it is not, in fact, snowing. So this isn't true. No. Right? So if that first one is true and the second one isn't, then these can't mean the same thing. What about if it is not snowing, then it is not cold? Well, just for the same reason, right? It's currently not snowing. But, like I said before, it is cold. So that's not true. So again, it can't mean the same thing as the original if it has a different truth value. Now, if it is not cold, then it is not snowing. In other words, if it's warm out, it's not going to be snowing, right? I mean, I know there's some freak weather out there, but just in general, that's generally how it works, right? If it's not cold, then it's not snowing. So that one makes sense. Now, just because both this first one and this second one are true doesn't necessarily mean that it means the same thing, but it's a lot closer to meaning the same thing. So let's actually look at the truth tables to show whether or not they're equivalent, though. So here I have my P's, my Q's, my negations all together, and each of these statements. So first, our conditional, we know, once again, the rule is if we start true, end false, that equals false. Like, that is going to be the rule for all of these, because all of these are conditional statements. It's just we have the original conditional versus the converse, inverse, and contrapositive of that original conditional. So this is what we're looking for. So here we've got column 1, column 2, and our starting true, ending false happens in the second row. Next, if this is column 2 and this is column 1, then our start true, end false actually happens in the third row. Next, we get if this is column 1 and this is column 2, then starting true and ending false is third row once again. And then negation of Q implies negation of P gets us this is column 1, this is column 2, and we have starting true, ending false in our second row. So notice which are equivalent. The conditional is equivalent to the contrapositive, and the inverse is equivalent to the converse. So this is a very important concept to understand because it's one that gets mistaken a lot. We often think, if we go back to my original example about the conditional, where your parents say, if you eat your vegetables, then you get ice cream, we often assume that if you got ice cream, then you must have eaten your vegetables, and that's just not true. That's the converse, and it's not necessarily true. Because your parents might have given you ice cream anyway. Remember how we went through those examples, those cases? But saying if you don't get ice cream, then you didn't eat your vegetables, that works out. That one is true as the original conditional. All right, so let's see this with some more written out verbal statements. So you're going to have to be able to convert into each of these different types of statements, and you're going to have to remember which is which. So make sure you internalize which is which. The inverse is both are negative. The converse is flipping their direction. The contrapositive is doing both of those things, which are equivalent. It's always the original and the converse. The original and the contrapositive. The converse and the inverse are then equivalent to each other. This is always the case. Remember this. Commit this to memory. So, if my statement is, if the painting is by Andy Warhol, then the painting is valuable. We have P is the painting is by Andy Warhol. Q is the painting is valuable. So the converse, we're just swapping the order we say this in. If the painting is valuable, then the painting is by Andy Warhol. Well, obviously that can't mean the same thing because, look, Andy Warhol was a famous artist, so yeah, his paintings will be valuable. But just because a painting is valuable, it could be by any famous artist, right? It doesn't have to be by him. And that's what this statement would imply, so it can't mean the same thing as the original. Next, the inverse, we're negating both but keeping the order. So this will be, if the painting is not by Andy Warhol, then the painting is not valuable. Once again, what if it's just by some other famous artist? If it's a Picasso, it's not by Andy Warhol, but it's probably gonna be valuable, right? So this doesn't make sense to mean the same thing as the original conditional. Finally, the contrapositive. We take the inverse and flip-flop it, or the converse and change its, and add some knots to it, however you want to think about that. So, if the painting is not valuable, then the painting is not by Andy Warhol. That one actually does make sense. If it's not valuable, if this is a worthless painting, it's not going to be painted by any famous artist, so it's definitely not going to be painted by Andy Warhol, right? And so that is our contrapositive, and it does in fact mean the same thing as the conditional, essentially. So make sure you're, committing to memory, like I said, what each of these means, and which ones are equivalent, because it only makes sense for some of these to be equivalent, right? We can figure out why these are equivalent to each other, because these have different meanings, right? So if you're ever confused on which one is equivalent, you don't have to memorize it. Don't just work on memorizing it. Think about what it means. If this is true, then this is true. They mean the same thing.